a lot. Thanks a lot for the nice invitation. It's really a great pleasure to be here in this nice place. Today I'm talking about equivariant formality reduction, meaning, just to give you a very, very rough idea, what I want to explain, to study here is a little bit the relation of reduction and quantization. But maybe for you these are still some buzzwords. So let me start with a dictionary. So what do I mean by reduction? So what are, let's say, the ingredients of this theory? So we do start with a Poisson manifold. So smooth manifold, bivector field defining a Poisson bracket. And why we do that, and this bracket is a Lie bracket plus Leibniz. And why do we do that? We do that because this bracket allows us to write the Hamiltonian vector field, the Hamiltonian equations of motion, even though the phase space is a generic manifold. Okay, but you know, I mean, dynamical system can have more information, can have symmetries, for example. And we know that from Noether theorem, there is a very good connection of conserved quantities and symmetries. So what's the idea of reduction? The idea of reduction is, let's cut away the symmetries. And this is very convenient because at the end of the story, of the process, you will get a smaller phase space. So you really can define dynamics, describe dynamics, reduce less variables. Very nice. So let's see how we do that. So how we actually describe symmetries. Symmetries for me is described by an action, a Lie group action. It's moving. And this action has to preserve my Poisson structure. So we're really preserving the dynamics in this sense. So this is what I call Poisson action. Plus, I need more. I need this action to allow a momentum map. Momentum map is just a linear map from M to G star, where this is the Lie algebra of my Lie group. So this is what I call J, momentum map. And from now on, I will talk about Hamiltonian action whenever I have a Poisson action plus J, momentum map, and they have to satisfy couple of things. So first, the fundamental vector field of my action has to be a Hamiltonian vector field. This is just the pullback of my J. So it's really a function on my manifold. Second, J has to be equivariant. keep in mind what equivariant means, because I mean, this is somehow the title of my talk. Equivariant to me always means intertwining the action. Okay, so here, for example, intertwining the action means that you have your Lie group action, and here you have the coadjoint one. Or if you want to, let's say, rephrase in terms of your pullback, so your J can be also rephrased in this way. It's a little bit an abuse of notation, of course, because I call it with the same name, but okay. This is sometimes called co-momentum map. So this has to be a Lie algebra morphism. Okay? It's the same thing. It's equivalent. So this is what I call Hamiltonian action, and this is the ingredient I need to cook up reduction. So let's see how do we actually cook up reduction. So what we do is we take a constrained surface. Let me call it C, just the preimage of a regular value of my J. It's called C for, let's say, maybe historical reason, because it's a coisotropic submanifold. So it's a submanifold. It's even more, it's closed embedded, it's really nice. Well, I mean, I'm cheating, of course, a little bit. I mean, I have to be careful with the action. I have to ask some topological things like proper M3, otherwise the orbit space can be completely nuts. We don't want that. But let's say under suitable assumption, everything works pretty nicely. We have a submanifold, and we can perform reduction. So theorem, maybe here. So if I now consider the following orbit space, I can really consider this orbit space because G acts canonically on C. This really comes out of the fact that J is equivariant. So this is not only a manifold, but it's a Poisson manifold. So this is exactly what we were looking for. This is exactly the reduced phase space, the smaller phase space we were looking for. So if you want to give to have a picture in mind, so let's think in that way. Imagine you have something like this is your big manifold, M, okay? And now you take your constrained surface. Let's use colors. This is your C. And then on C, what you have is also the action. So you have a characteristic distribution given by the action. I don't know, something like that. And clack, you can project. And you have your reduced manifold. So that's just to have a picture in mind, okay? So you see, it's very convenient. It's really nice. So we would like to know what happens under quantization. Let me just give a name because we will need later on. I'm not saying who did this theorem. I mean, the original version is by Marsden and Weinstein, but was in the symplectic case, and then there were a lot of extensions by Tudor-Razio. I mean, okay, many people worked on that. Okay, so we would like to understand what quantization, what happens under quantization. Point is that we don't even know what quantization means right now. So let's define it. Let's talk about quantization. So buzzword number 2. Okay, quantization. What do I mean by quantization? There are different procedures, but what I mean is deformation quantization. So what is the philosophy of that? Philosophy is, let's consider a classical algebra, and then we want to find a suitable non-commutative one, which is a deformation of the classical one. Let's say this is a program, has many advantages and also many disadvantages in quantization. But okay, I mean, let's say what we like about this program is the fact that if you think in terms of physics, even though, I mean, this is just a far motivation, the physical observables in the classical and in the quantum setting are the same, which is nice. So we can directly compare. Okay, but so let's focus on the math point of view. So my classical algebra is what? Yes. Smooth functions on my manifold that, remember, was a phase space, pointwise product. But also, don't forget here, we have more. We have more information. We have something that allows me to describe dynamics, the Poisson structure. So I want to cook up a deformation of this, really in the sense of Gerstenhaber. So let's say for my background, the product here is the deformed product, and this is what I call star product, okay? So you see formal power series. So star product is what? Star product is, as I told you, deformation of the classical one. So formal power series starting with m plus whatever. Well, not really whatever. Let's think a bit what we have here. So requirement number 1, let's say, is let's say the direction in which I'm quantizing, because I want to involve a little bit the Poisson structure. So I want M1 to be related with pi. So I write equal, it's not equal. I have to symmetrize, but okay, I mean, let's say equal. Requirement number 2, MK are bidifferential operators. Okay? This really comes again from motivational physics. We want to somehow recover the locality behavior of quantum mechanics. So that's why we focus on these specific ones. And then, of course, requirement number 3, that maybe should be requirement number 0, is the associativity. And this is, let's say, not a nice thing to check, because if you really try to check directly over there, what you get is an infinite chain of quadratic equations on MK. So can we actually do that? Can we really do this passage? Luckily, yes. Luckily, Kontsiewicz, thanks to Kontsiewicz, we can say yes. So theorem. Sorry?
The order of those is 1 or is it k?
No, it's k, it's k. This is T2, right? Yes. Okay. So formality theorem tells me that there is an L-infinity quasi-isomorphism connecting poly-vector fields and poly-differential operators. So I know, I mean, most of you know exactly what happens here. I just want to refresh a little bit what happens also because I have to focus on some aspects that I need then to extend to equivariant formality. And I've seen that most of you, I mean, have different formality in mind. So I want to different kind of formalities in mind. So I want to refresh a little bit. So why this theorem actually solves this question? The point is the following. I mean, what we are trying to do is connecting, remember, essentially a bivector field with those bidifferential operators, right? Okay, so let's say we like this arrow. Good, but why we actually need the fact that this is an L-infinity quasi-isomorphism? And how we get it, let's say very, very roughly, I mean, long story, very, very short. Keep in mind the following. So what is this, guys? A bivector field? Yes, but that's a special one. It's a Poisson structure, right? So Poisson structure is equivalent to say that this is a Maurer-Cartan element in this complex, in this DGLA. And same story here. Essentially, associativity of star means that this is a Maurer-Cartan element. These are Maurer-Cartan elements of my DGLA of poly-differential operators. So we want to connect Maurer-Cartan elements. So that's why we want to have something like that. So the idea is the following. We take the poly-differential operators, compute its cohomology, bang, we get the polyvector fields. Enough? No, it's not enough. We need more. We need to connect the Lie structures, right? So, I mean, the HKR theorem is not enough. We need more. So Kontsiewicz proved that you extend, let's say, HKR theorem, you get more Taylor components, but they really connect differential and bracket in a way that we actually get what we want, okay? So as I said, very short way to say what formality is, but it's good to have this in mind. And now you see, I mean, I have my two words in mind. So reduction and formality. So this is what I mean by quantization. And also try to keep in mind that somehow whenever I talk about this side, so bivector field, in my eyes, I'm talking about the classical side of the stories. And here I am talking about the quantum version of the story. So this is really the quantization. But I can also talk about the classical part and the quantum part somehow independently. Okay, so I will now try to cook up the diagram of quantization and reduction, or formality and reduction, in a rough way, just to give you a little insight, and then we go through. And maybe it's good to have it here. So let's say chapter number 2, diagram. Okay, we have to be careful, we have to make some steps here. So step number 1, how can I compare formality and reduction? Because reduction, what I told you, is just a geometrical construction, just a theorem in differential geometry, in symplectic Poisson geometry. So the idea is, what we did is, let's try to rephrase this arrow, the arrow that takes my manifold, my Poisson manifold, and gives me the reduced one in terms of L-infinity morphism. Okay? So I really try to rephrase reduction, or make a reduction scheme in terms of L-infinity morphism. So, and of course, I have to be compatible with Poisson reduction. Okay. So, the idea we had is the following, very rough. Let's construct a DGLA that encodes all the information of the Hamiltonian action. So this is what I call TG. So it's a new complex. You will see this is really, morally speaking, you take the polyvector field and you have to extend it in a way that incorporates the Hamiltonian action information. And then I want to go to the usual T-poly complex, but on my reduced manifold, okay, via an L-infinity morphism. So this is, let's say, step number 1, which is also, let's say, paper number 1. And same story on the other side. So, of course, here you don't know very well what does it mean encoding Hamiltonian action in the game, but I will try to explain you. But morally, the philosophy is the same, okay? And now, what is this? This is just a Poisson manifold, okay? So this is just formality for this specific manifold. So step number 1 is this one. Step number 2 is this one, is this vertical arrow, and then we have this one missing.
You're asking for an L-infinity quasi, right?
These ones are not quasi.
Now what are they?
These are L-infinity morphism curved. Okay?
Neither isomorphism or normal property?
No, no. And this is also what makes more complicated the future story. So, step number 3, this horizontal arrow. So we have really to try to understand whether there exists a formality for these specific extensions. And we have to be very careful. You will see, I mean, here we have some extra structure. We have a curvature, as I was saying. I mean, now this is still very vague, but you will see very clearly how this enters in the game. So this is, yeah.
Can you say what the Morgan elements in TGM?
I will prove you. Okay. So give me 5 minutes, and I will. Yeah. No, that's actually the crucial part of the story. I mean, the Morgan elements here essentially are the Hamiltonian structures. So, G-invariant Poisson structure and momentum map. But I will show you a bit better. Okay, so step number 3, equivariant formality. Okay, this is something that has been conjectured, I don't know when, many years ago by Boris Tsigan. And as many of you actually already know, thanks to a stay in Obavovak recently, this has been proved. Yeah. Okay, so, and of course, now the question, and this is really future, is what happens to this diagram? Can we actually say that this is a commuting diagram? The problem is that, I mean, let's put that way. I mean, morally speaking, I would expect that it commutes up to homotopy. Problem is that you will see that these are curved DGLA structures. And in this setting, I don't even know what homotopy means. So I can tell you at the very end of the talk, what is the interpretation, let's say, of this commuting diagram? What do I have in mind with homotopy? But this is still in progress. Okay, so now just to, let's say, to start understanding a little bit better what's happening over there, I have to define these complexes, what I call the equivariant complexes. Oh, I'm short. Let's see. Okay, so as I told you, what I want to do is, let's start with this part of the story. So with the equivariant multivector fields, I want to encode the information of a Hamiltonian action. So remember, okay, it's over there, but let me remember you essentially what is crucial for us. What is crucial for me is I want to encode the information of the infinitesimal action. Okay, so the fundamental vector field. Okay, so this is xi, and this is the fundamental vector field, where that has to be Hamiltonian. So this is what we want to do. So the idea is now to define a complex that, as I said, extend the polyvector fields in a way that this becomes a canonical element. So let's define this complex. So what do I want? So let's take T poly. And then think I want to get this kind of maps, right? Some polynomial maps. So easy way. I tensor for the symmetric algebra of the dual. And I want everything to be invariant under the action. Okay? This is my complex. So it's very easy to give it an interpretation because you see it's really polynomial maps. Of this kind. Polynomial maps, equivariant. Okay? Equivariant, you see, again means intertwining the action. So equivariant now means adjoint and push forward action. So this is equivariant here. I have my complex, so let's see what kind of DGLA structure I can put on it. So, well, let's say if you think in these terms, it's very easy because I have a DGLA structure over there already. So I just use it. So D is 0. And the bracket, I just look on the image. This is Schouten bracket. Okay. So far so good. But you see, I mean, we do have a canonical map. We do have a canonical map because this is really, remember that, I mean, when I say J here, I mean J plus 1 polyvector field. There is a shift in the formality. So this is actually 1 means T poly 0. Okay. So I give it a name because it's an important object. I call it lambda. Okay. And what I can see is that this lambda is a central element. So what I get at, after all, is a curved DGLA. So you see, curvature is important because it really has inside the information of my action. Now, as I was asked already, what are the Maurer-Cartan elements? Now, Maurer-Cartan are actually curved Maurer-Cartan elements. Okay, so you have your lambda plus differential is 0 plus 1/2 of your bracket. And here you can actually prove that the curved Maurer-Cartan elements are exactly what we want to describe. So they are equivalent to the pairs pi j, where pi is a G invariant Poisson structure, and j it's a momentum map, equivariant momentum map. I don't have time to prove it, but I can show you later on if you like. This is really 2 lines proof. This is really nothing. I mean, just split the Maurer-Cartan element in these 2 legs, and you will see. I mean, if you fix the degree 1, it's very easy. But now remember what we had in mind at the beginning when we talked about reduction. At some point I told you I want to take this, fix this constraint surface, right? So I want to choose a momentum map and fix C to be this one. So let's say so we choose a momentum map and we fix the constraint surface. So in order to, let's say again, to implement this choice in our algebraic setting, what we have to do is twisting our DGLA structure. So from now on, when I talk about the equivariant complex, what I have in mind is the following. So I have G. I have my lambda, the curvature. And now not 0 anymore. I twist it. Via Maurer-Cartan element. No problem, we can do that. We all know that very well. So this is my complex. And when I will try to explain you a little bit, okay, roughly, this arrow, you will see that this choice is really also, I mean, I don't know how to say it. The choice gives us some acknowledgement, let's say, let's put it that way. Okay, so this is the complex I need to have in mind. Now, same story for the equivariant multivector polyvector differential operators. So I don't want to be too precise, but just to so what we want to do, I mean, we want to use the same, let's say, the same philosophy here. The point is that I have to understand what do I want to include in the complex. Okay, so we remember what I told you at the beginning. I mean, let's say classical side, quantum side. So quantum side to me means star product. Okay, so what I want to inject in the DGLA is the following. So take a star product, which is G invariant.
Sorry.
Yeah.
I'm
Sure.
a bit confused about this G minus 1. I mean, it should go in the wrong direction. Is it G? I mean, you did
This one, sorry.
G, like Kerr-Maurer-Cartan element, going from the Lie algebra to the
So you're right, because this is, you remember I told you there was an abuse of notation at the beginning. You remember when I say this one, you're right, sorry. I mean this object, right? So this is really a submanifold of M. And then when I say this one, this is, I don't know how to call it, this is actually a pullback, okay? This is, I don't know, thanks. Okay. So we have this one here, G invariant, and I want to have, yeah, sure. Sorry. Clearly, formal power series. Of course, I'm cheating here because I didn't extend to formal power series, but believe me, that's not a problem. You have a complete filtration by the degree of H bar, so that's not a problem, so you can do that. Okay, so this is star product, and now I consider, again, a linear map now to formal power series. And now, very similar story. What is, this is actually a quantum momentum map. Whenever it satisfies something very similar, it's not there anymore, to what happened before. So I need to, let's say, rewrite the action. You also have, well, you have a G action, of course. Now, the Lie derivative along the fundamental vector field is Hamiltonian in this sense. So star commutator of this object. And you have a sort of equivariance. So this is a quantum momentum map, and I mean, if let's say my star product allows that, we call it equivariant star product. And now, same story. So we really cook up sorry, same story. First, we can perform a reduction with these ingredients. And second, now we define a new complex in the very same way, so extending d poly with this, let's say, the same spirit. We have a curvature, which is again the action. Now this action. Now here, you remember we are in the d poly case, so we have the Hochschild differential. And also in this case, we twist it. Wait. No, you're completely right. Why J? Because H is a deformation of J. Okay? Makes sense. It's central, everything works. Okay. So you see, we have the two complexes. And now I can really try to perform out of these complexes the two vertical arrows. Maybe it's a good idea to come back here. You can see I spent many years in Germany, right?
Can I ask you to move the blackboard behind?
Yeah, you're right. So this is the number 2, right? Yes. Okay, and now, very roughly, I can tell you, let's say, what is this vertical arrow? I mean, the philosophy of this one, the philosophy of this one is very similar to the first one. So, So this R is a curved L-infinity morphism. Okay, I don't have time to prove it, but I just want to sketch a little bit the strategy. So, the strategy somehow copies what happens in the symplectic case, where they actually construct a Cartan model. Meaning what? Meaning you construct R by looking for something which is an intertwiner. Okay? And then invert this arrow. and compose. So, what can be the intertwiner? So let's say we have a very easy educated guess, which is the cohomology of this. So we compute this cohomology. And now you see, I want to just to stress, you see, it's very nice. Here, the only part of my manifold that appears is my constraint surface. And this really depends on my choice of the differential.
I think I heard you said this is the homology of these two guys?
No, this is, no. This is the homology of this one.
Okay.
I'm cheating, you will see why. So let's say, okay, forget a little bit the DGLA structure at the moment, okay? So just think on this differential, and you have this guy. And this will be the canonical inclusion. Yeah, let's say so. And then this one, I mean, from the graded vector space, will be just a projection, right? Which is a very easy one. I mean, just have to project on the grid 0 here, and then really project from C to M red, so the projection in the sense of a quotient. No problem. But the problem is that we are completely forgetting the structures. Okay, so there are many problems here, let's say, that we have to fix. Well, many. Let's say 2. So this is a quasi-isomorphism. This is a DGLA quasi-isomorphism, but with respect to what? The point is that here the differential is 0, because it's a cohomology, right? So it connects 0 and this one. Other side, it's not true anymore. So P is not a DGLA morphism connecting 0 and 0. What we can do is somehow there is a canonical differential you can actually construct over there, and P is a DGLA quasi-isomorphism with respect to this one. So this is problem number 1. We have to adjust it. So how to correct the structure? We do correct the structure by twisting again, essentially. So we are kind of lucky because we have a canonical element in this complex, that allows me to twist this differential in a way that cures this problem. So, and this comes out of a linear Poisson structure. You don't care about what it is. It's a Morar-Cartan element. I can twist it, and I have what I want. So first problem is solved. Second problem, even more important to me, is the curvature. Because when I compute the cohomology, here I had 0. And this is not what I want. I want to have lambda. And also, I don't want to have this extra funny guy here, okay? So what do? Let's say the strategy, very roughly, is the following. Okay, we can prove that this is a quasi-isomorphism. We can invert it. We can invert it, compose it, and we get our R. Okay? Connecting these graded vector spaces. So you get your R, but then you have to adjust the structures. So first, you twist it back. And twisting back, well, first gives you back the differential you want, but also has an effect on the curvature. Problem, let's say, is that it has an effect also on the other side. Let me call it sure, it transports it. So here there is a lot of, I would say, deformation retract gymnastic. Okay? Because essentially what you do is when you invert this one, which remember, when I invert, I don't take care of the curvature. When I invert this one, I can really construct concretely a formula for the inverse via deformation retract, which is very nice. So I do it in a way, I tune it in a way that kills me this guy. Clack, got it. So, okay. So, so this is more or less very roughly the strategy. Actually, I mean, there are many things to say. Okay, well, maybe not a good moment to say more. But let's say with the same kind of strategy, you also get the second theorem. So let's say okay. Let's say the techniques are more involved. It's a bit harder, but the strategy, the philosophy is exactly the same. You have to cook up an intertwiner, okay? And you have to readjust the structure in the way you like. Okay. So far it's good because you see we have finally got this arrow and this arrow. And just to connect to the question Bruno asked me before, it's when you go inverting, you get an L-infinity morphism, not a quasi-isomorphism anymore. So that's why R is not a quiz.
I'm confused. What is the statement of the theorem?
The statement of the theorem is that there exists a curved L-infinity morphism connecting these two complexes, R.
In white too. With the white too.
With the?
White.
With the white.
Yes. Yeah.
Could it be a weak equivalent in the following sense? So, okay, we cannot ask for it to be a quasi-iso because it's curved. In the curved world, we can ask that it's bijective on the sets of more Cartan elements.
It is.
Local.
Yeah. Thanks. Thanks for pointing out.
This is the nice statement. I mean, this is the correct homotopy property.
Yeah, exactly. Okay. Yeah, you're right. Very good point. Thanks. Thanks for pointing out.
Is there some filtration happening?
Not yet, because I don't have a formal power series here yet. But if I inject, yes.
And for these curves and infinity morphism,
No problem. I mean, as I said, this is complete filtration. Okay. So, sorry? This I don't know. I don't know. I have to think. Okay. So last 5 minutes. Let's go to equivariant formality. Last step. Okay. Maybe. Do I need? Oh, okay. Let's do it. This is number 1. Okay, now we have really all the vocabulary to understand what was, let's say, the conjecture of Ziegen and what was the question, essentially. So the question is, given a G-invariant Poisson structure, admitting a momentum map, equivariant, can we actually prove that there exists an equivariant star product? So really a star product which is G-invariant plus admitting a quantum moment map? And the answer is yes. So can we really go from this object to this object? And the answer is yes, because now we can prove equivariant formality connecting exactly the two complexes having those guys as Moore Cartan elements. Okay? Okay, so very roughly, what is the strategy here? And what is the tricky part? The tricky part of the story is the curvature that we really want to preserve. So we really want to go from lambda here, which is my action in the classical part, to my lambda here, which is my action over there. Because you see, I mean, intertwining the action, this is equivariant formality. Okay, so what is the rough idea of this proof? So we start with something with a formality which is G invariant. This is not a problem. We can do that. I mean, let's say what the part of the story I know is that when you prove formality, you prove the globalization. So from Rn to a generic manifold, there is different techniques, different procedures. What you can do, for example, is a beautiful proof given by Vasily Dolgushev. That essentially does the following. I mean, takes your DGLAs and resolve it a lot. So resolves in a way that the bundles you get are so big that the arrow among them is easy to cut to get. To do that, you can at some point have to make a choice. And the choice is choose a connection. So if you choose a G invariant connection, what you get is a G invariant formality. So no problem. And whenever you change connection, what you get is homotopy equivalent formalities. No problem. Okay, so first requirement. Well, I mean, remember that we have in mind for reduction as a motivation. So I have proper action. So I don't need compact, but yeah, proper, yes.
Sorry, so it's formality with respect to the original dipole and dipole of n.
This one, yes. This one, yes. Because the idea. Yeah, the idea is really taking the usual formality and extend it. Okay? But I have to choose wisely the formality I start with. So I start, as I said, with a G invariant one, and I start with a formality having the first Taylor component preserving the curvature. This I can also do, I mean, because this is essentially HKR, so not a problem. So we really start with something which is compatible with curvature. Remember that this is what I call from both sides lambda. Oh. And now what we can do, we essentially extend the formality map. If you remember, what are the complexes? Yeah. So this is now number 2. And this is now number 3. Yeah. So look at the face of this complex. I really have to extend my formality in an easy way, just adding some part like, let me write it. So this is the K-Taylor component. So how did I call it? P1. You see, this is my formality, and this is the way I extend to my complex. Easy. Okay. Now, problem is, again, what happens with the curvature? Because, okay, we started with this one, but what about the kth terms? We don't know. Okay. So what we prove is that actually the formality, F, can be extended to a curved L infinity quasi-isomorphism, well, morphism, okay? If and only if, whenever in the K component of my formality, I inject once a curvature, this gets killed. This is 0, okay? So essentially what we did is, first, proving this equivalence. So F can be extended if and only if you have this condition. Second, we had to prove that such an F exists. And then the equivariant formality is done. Of course, I'm cheating a little bit, because so far I only talked about curvature. I never talked about differentials. And in fact, I mean, the formality I cooked it up in this way still connects the old differentials. So 0 here and Hochschild here. No problem, we can twist it. So we twist by this one, and we know, I mean, by twisting, everything is very nice, very robust. So we had a quasi-isomorphism, we still have a quasi-isomorphism. Still involved with curvature, no problem. So the equivariant formality is proved. So just a 2 minutes comment, if I have 2 minutes, yeah. So now I can really explain you a little bit better what do I mean here. When I say, I don't know what haptohomotopy means in the curved setting, but I know what will be the interpretation of this. So this, I know, brings me to star product, G invariant, allowing a quantum moment map. This one I also know. It brings me to pi red, right? And now pi red also goes to star, I don't know, let's call it red. And this one also gives me another star product. I would like this, I mean, commuting this diagram will mean that these are equivalent. Okay? So this is still very, very much work in progress. And this opens a lot of new questions, of course. This equivariant formality opens a lot of new questions. I mean, what we are already working a little bit on is the chain version of this theorem, which is still really in progress. It's really unclear, but we are working on that. And we can somehow, well, as a very long goal, go in the direction of equivariant index theorem, algebraic index theorem. And I think I'll stop here.
Thank you. Are there questions to the microphone? And to Chiara? Yes.
All right. Hi. So another context in which there's both symplectic reduction, quantization, and the diagram commuting appears in this the geometric quantization and commutes with reduction program of Guillaume and Sternberg, etc. Can you comment a little bit on the relation between that, which uses geometric quantization, and this deformation quantization story?
Not, let's say not yet. I mean, what I can tell you is, well, first that geometric quantization is a very beautiful procedure, very strong. But on the other hand, I mean, it works on some examples and not in pure generality as deformation of like formality does. So in those particular examples, we can actually compare, what happens. But to be honest, I don't know. I mean, I know that, for example, the formality, let's say, business, I mean, the deformation quantization business in the symplectic case has been already done by Thorsten Reichert some years ago. And still, also in that case, and it's not very clear what is the connection. So I don't know.
I see, but in the symplectic case, it is known that this diagram commutes? No, it's not.
No. I mean, sorry, not this diagram, but yeah, there is a commuting diagram of reduction and quantization, yes.
I see, and that one, even that one is not known to commute.
It's a different, it's a different object because the complexes are completely different, because you don't go to polyvector fields, you go directly to forms, which makes everything way nicer because you can pull back. So, and in that case, yes. Yeah, it works.
Thanks.
Other questions?
Okay, can you view this as some special case of coisotropic reduction?
Well, this is a part of the project in some sense. I mean, myself, together with Stefan Waldman and a student of mine, Marvin Dippel, are trying to rephrase reduction in terms of coisotropic algebras, let's say. So really in completely algebraic setting. So we are trying to understand a bit better. Yeah, you can, of course, talk about coisotropic reduction, no problem. And there is the quantization part of that. We are trying to reformulate in a completely algebraic way. But again, the relation is not clear yet.
Questions? Okay, so let's thank Chiara again.